All right, so chapter 4 is all about chemical bonding. We're going to spend a lot of time on this, almost 2 weeks in total, and then tomorrow is going to be an in-class activity. So come tomorrow if you want some hands-on experience with understanding bonding. But before we talk about bonding, we have to review valence electrons. What are valence electrons? Yeah, they're the outer shell electrons, right? So let's take an example. Let's do something like lithium. We know lithium, by its very nature, has 3 protons, so I'll go ahead and draw 3 protons. It usually has 3 neutrons, at least for its most abundant isotope, so I'll put 3 electrons in the center. And lithium normally has a positive 1 charge. So we've got these inner shell electrons out here, and we've got these outer shell electrons out here. So this would be an example of lithium, which would be lithium-6. And we said that these outer shell electrons equal our valence electrons. And these tend to be the most reactive. How can we normally tell the number of valence electrons that an element has? The periodic table. What on the periodic table in particular? Yeah, the Roman numerals, right? So if we look at lithium, it's in group 1A. So we could say, hey, it's got 1 valence electron. That's the easiest thing to do to determine valence number. What about boron? 3. It's in group 3A, so we'd say it has 3 valence electrons. Yep?
You said it usually has a positive 1 charge, but there's no charge on this one?
Yeah, in this case, we're going to do elemental lithium. However, we will discuss ionic lithium later. Normally, it wants to get rid of that valence electron. However, we're not ready to talk about that yet. So let's do a little bit of review. We said that our valence electrons can be found by that Roman numeral. We said that it's your main group number, that Roman numeral in the table, and then minus your charge if you have a charge. And sometimes you run into situations where you have a charge and sometimes you don't, so if needed. So let's go through and do a few examples. I'll do total electrons, valence electrons, and then core electrons. And we'll try to use this formula to kind of help us out. So the first one we'll do is lithium. And we said lithium has how many total electrons typically? 3. Has how many valence? 1, which means we have 2 core electrons, right? So that was our first example. All right, let's do another one. Let's do magnesium 2+. How many total electrons does magnesium normally have? So let's ignore the 2+ right now and just say normally magnesium has how many?
12.
Yeah, normally 12 in order to balance out the protons. However, in this case, if we have a 2+ charge, how many total electrons do we have? 10. Okay. How many valence electrons do you think magnesium has?
2.
It normally has 2, but if we take away 2 electrons, so we would say 8 or 0. I'd be fine with that either way. Let's do 0 in this case. So we took away those 2 electrons that were normally there in that valence shell, which means we've got 10 core electrons. That's another way of thinking about it. Let's do nitrogen. How many total electrons does nitrogen have? 7. Okay. Valence number? 5, which means we've got how many core? 2. So you guys can kind of go through and plan this. This is really similar to that table we had on our first exam, being able to predict how many electrons we have. But now we're primarily concerned with these valence electrons These core electrons don't really do much. They just hang out. Does that make sense? Okay, so we have to represent this using special symbolic representations called Lewis structures. Has anybody done Lewis structures before? A couple people? So Lewis structures are really, really simple and straightforward, and we're going to use them a fair amount. The easiest thing to do with Lewis structures is represent electrons as dots. Oh. Actually, let me rephrase this. Represent valence electrons as dots. We're going to ignore core electrons. And the rules are super simple. Add 1 dot per electron. Second rule is go one side per time. Then pair, and I'll show you guys what I mean by that. So let's say I've got an element symbol, and I'm just going to call this element X. And let's say this symbol X has, I don't know, let's say 6 electrons, 6 valence electrons. Okay, so maybe it's oxygen, maybe it's sulfur, maybe it's selenium. We really don't know. But what we want to do is represent this in Lewis dot structure. So we go ahead and we'd say, all right, 1, 2, 3, 4. So we filled out all 4 sides. And then we start pairing. We go 5 and then 6. So this would be the correct Lewis dot structure for something with 6 valence electrons. What I don't like to see is somebody say, all right, 1, 2, 3, 4, 5, 6. That looks funny, right? Or to see somebody go 1, 2, 3, 4, 5, 6. You only want to have electrons in pairs of 2. They can be either solitary electrons or paired electrons. You don't want to see electrons with 3. Does that make sense? Let's do a few examples. Let's do lithium. Let's do oxygen. Let's do magnesium 2+. And let's do carbon. So how many valence electrons does lithium normally have? 1. And there's no charge. So how many valence electrons does it have? It's got to have 1, right? So this one's easy. Lithium dot. Easy enough. Oxygen normally has how many valence? 6. There's no charge, so they all have to be included. So I'll go oxygen 1, 2, 3, 4, 5, 6. That works. All right, magnesium. This one's tricky. Magnesium normally has a valence of 2, but it's got a 2 positive charge, so it'd be 0. So we would just write the element symbol with no dots on it. So let's make a note of that. So 2 electrons were removed. Okay. And then for our next one, we've got carbon, my favorite element. How many valence electrons does that have? 4. That's one thing that makes carbon so special on the periodic table, is there's a whole branch of chemistry dedicated to carbon, that's organic chemistry, simply because carbon can form 4 different bonds with neighboring atoms. It's got 4 unpaired electrons that are very, very reactive. That's why it's the basis of pretty much every single biomolecule. Does that make sense? Let's do one more. Let's do argon. So AR. What's the valence for argon? 8. So if we go through and we fill this all out, we go 1, 2, 3, 4, 5, 6, 7, 8. Argon is very, very different from carbon. We said electrons like to be paired. This one has all of its electrons paired. That means argon is very special and stable. That's why we call it a noble gas, is it doesn't want to react with anything else. It's very content in its electronic configuration. And this leads to the next section called the Octet Preference. And I don't like the term octet rule. A lot of people use the term octet rule. They're really more just guidelines. If you guys have ever seen, what was that movie with the pirates? Pirates of the Caribbean? Like the Pirates Code, it's like, oh, they're really more just guidelines. And this came from a set of observations, primarily based off of the noble gases. So noble gases are inert. What does inert mean? Non-reactive. So inert means non-reactive. They kind of just sit there and stare at everything. And they have 8 paired electrons. So the key thing is that they have 8 electrons. Because they've got a filled valence shell, they're very happy and stable. So the theory was based off of this, and it said their stability is due to having an octet, or 8 electrons. Makes sense? All right. And that leads to a deduction. Other elements really, really want to become stable, so they want to gain or lose or share electrons so that they too have an octet of electrons around them. So that they have an octet. Oh, my pen's dying for some reason. So in the case of magnesium, magnesium wanted to lose electrons. There are some that actually want to gain electrons and others that simply want to share them. And we'll talk about each of those classes. Does that make sense? It's a pretty simple theory. But in order to understand this, we have to talk about something called electronegativity. And you guys don't have to copy this table down unless you want. But if you go on Google and you look up electronegativity, you might see a table like this. Looks like the periodic table, but it's got numbers in the top right-hand corner, or in the box. In this case, what you may notice is that the most electronegative elements are red, and the least electronegative elements are blue. So the trend is essentially going towards that top right-hand corner towards fluorine, right? This is a really important trend to remember. It basically says everything gets more electronegative the closer you get to fluorine on the periodic table. Fluorine's kind of the gold standard for electronegative elements, no pun intended. However, it's important to note that these aren't electronegative. Why aren't they? Yeah, they're already happy. They have 8 valence electrons. So this table helps us determine how badly an element wants electrons. That is exactly what electronegativity is. So fluorine really, really wants electrons, but if we go over to sodium, Na, that's got 0.9. Sodium doesn't really want electrons very much. Yep.
So does electronegativity correlate with the strength of the bonds?
Kind of not. It really depends. That's a somewhat complicated question. If you go on in chemistry, you'll talk about that a lot more. So for example, carbon and fluorine bonds are very, very strong, but carbon and iodine bonds really aren't. It gets a little bit complicated. Yeah. So this table is super duper handy, and we're going to use it a fair amount. But there are some basic trends I wanted to bring up. If you have two elements, and there is a large difference in En, or electronegativity, then there will be a theft of electrons. Whoop. This is a key thing to remember. So let's take an example of this. I'm going to zoom out a bit. Let's say I have sodium, which is 0.9, and I've got chlorine, which is 3.0. That's a difference that's what, 2.1? That's a very big difference in electronegativity. That means that chlorine is essentially going to steal an electron from sodium and form a compound called sodium chloride. Does anybody know what that is? Salt, table salt. So this is typically how we define ionic compounds, and we're going to spend a chunk of time talking about this. If there's a really small difference in electronegativity, we end up not stealing electrons, we end up sharing electrons. I'm just going to abbreviate electronegativity as En. So if there's not a huge difference, they're content just sharing them. There doesn't need to be any stealing. And this is called a covalent bond. The way I typically remember this is the co in here means that you're sharing, right? So a coworker is somebody that shares a workspace with you. A covalent bond is a bond where you share electrons. All right, so what we're going to do with the remainder of this class period is talk about covalent bonds exclusively and put ionic bonds kind of on the back burner, and we'll cover that later on in the week. So let's define covalent bonds in a little bit more detail. So we said covalent bonds occur when there's a sharing of electrons between two atoms. And we said that this typically occurs when you've got a small difference in electronegativity. And then I'll show you guys the easiest way of remembering what a covalent bond is too. But let's finish these notes. Between two atoms. So small difference in electronegativity. And it usually occurs between nonmetals. The way I typically remember where nonmetals are is that they're usually on the right-hand side of the periodic table, right? If you remember back to our periodic table section, we said most of the stuff on the left-hand side is metallic. But if we look at group 3, so Roman numeral 3A and over, those are typically our nonmetals. So typically it's from group 3A to 7A. Why don't I have 8A in there? Yeah, noble gases we know are kind of happy on their own. There are some exceptions to these. These are just rough guidelines, so take that usually into account. I'll show you guys how this works. It's pretty dang simple. We're going to start out with Cl2. This is chlorine gas. You guys want to hear a weird trivia story or history story about chlorine? So, did you guys study World War I at all in high school? A couple people did. I know it's kind of hit or miss depending on high schools. But chlorine gas was the first chemical weapon used on the battlefield, and it was really horrendous. There was this chemist named Fritz Haber who won the Nobel Prize for a completely separate thing, who enrolled in the German army and said, you know what, what's the difference between a bullet and a chemical weapon? It doesn't matter, people die, right? So he went out and, his dress blues and whatnot, strolled out to the front line on his car, got a bunch of chlorine gas cylinders, opened them all up when the wind was right, and this big chlorine gas wave went and hit all the British troops on the other side. When chlorine gas hits your lungs, essentially it will blister your lungs and your eyeballs, and the soldiers all freaked out, as you can likely imagine. It didn't kill very many soldiers, but it really, really terrified them, so it was a very effective psychological weapon. The problem was the Germans thought, hey, we'll scare them out of their trenches, and then we'll just run into their trenches and steal their line, right? Problem was the chlorine gas lingered, and the Germans were too afraid to even go in after they had deployed their chemical weapon. So it was a really crummy weapon, and it was a part of the reason why we developed the Geneva Convention, was to avoid the use of these really horrendous chemical weapons. Yep?
Is that called mustard gas?
No, mustard gas is a little bit different. It has a sulfur in it. So with the chlorine gas, the weird thing about this is Fritz Haber did this. He felt, I'm a chemist, who cares? I killed people with a gas as opposed to a bullet. That's my thing. He went home, and his wife was also a chemist, and she said, you did what? She got so upset with him, she ended up committing suicide, and his son later ended up committing suicide too. So he's this pariah in the chemical community. He was an amazing chemist. He's responsible for artificial fertilizer production that saved billions of people, but he's also the father of chemical weapons. So dark history there. Sorry, that's my own side story. It's been, I think, almost 100 years since the first use of chemical weapons, so you might hear about it a lot in the news. So let's do the Lewis dot structure for chlorine. How many dots should be around one chlorine atom? 7, right? It's in group 7A. So I'll do one chlorine here. I'll go 1, 2, 3, 4, 5, 6, 7. Okay? We know we've got 2 chlorines based on this subscript 2 here. So I'm going to put another chlorine over here. This one should also have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. What's the difference in electronegativity between these two? None, right? They're identical. So they have no difference in electronegativity. That means they're more likely to form a covalent bond, meaning they want to share electrons. So if we look at these, which electrons do you think are likely to be shared? Yeah, the middle ones. So we'd say, if we were to draw this, we could say those center 2 electrons are a bonding pair. They're being shared. And then out here, we've got all of these electrons that are still hanging off the chlorine. Does anybody know what they're called if they're not participating in a bond? Called a lone pair. You can imagine them as loners, right? They're just kind of hanging out on their own. So you can represent Lewis dot structures this way as well, where you've got the dots shared between 2 different elements. Occasionally what you might see is something that looks like this. You can also show bonding pairs as a line. But this line can only have 2 electrons, right? Yep.
The lone pair is only the one at the top right. It's not the other.
No, all of them are lone pairs. I should have been more specific. Yeah, all of these green circles are considered lone pairs. Any bonding pair of any pair of electrons that's not participating in a bond is considered a lone pair. Does that make sense? Do you have a question?
Yeah. How can electrons bond with each other if they're both negative? It's not like they would repel.
That's a good question. So your question was, why do 2 electrons want to be close to one another if they have similar charge? That gets into more advanced chemistry. So electrons have a thing called spin. They can be spin up or spin down. They are really happy being paired as spin up and spin down, and that's the attractive force between them, and that actually overcomes the electronic repulsion. But it gets into kind of complicated chemistry. If you go on and take Gen Chem, you'll talk about it a lot more. Let's do another one, also related to Fritz Haber. So I said he was notorious for deploying chlorine gas and killing all these people, pretty complicated guy. But he's also responsible for creating ammonia artificially, which is essential for crop production. It's used in fertilizers. Prior to the invention of artificial ammonia, the capacity for us to grow enough crops limited our population to about 2 to 3 billion people. Without his invention, we would have had mass starvation and famine in the 1900s. But we were able to produce this artificially with his invention. So let's do the Lewis dot structure for ammonia. And let's have nitrogen be in the center. How many valence electrons for nitrogen? 5. Okay, so I'll do 1, 2, 3, 4, 5. All right, and then we've got 3 hydrogens. I'll put a hydrogen over here, over here, over here. How many valence electrons? 1. It's pretty easy. It's in group 1A. Put 1, 1, 1. We know that these want to be paired. The difference in electronegativity is pretty small. They're both nonmetals. So maybe we can pair those 2. Then maybe we can pair these 2. And then maybe we can pair these 2. Okay, so now let's turn this into a basic Lewis dot structure. And there we go. This would be our Lewis dot structure for ammonia. What would we call these up here? The lone pairs. They're not participated in bonding, where the bonding pairs are the shared electrons, right? Let's do another one, and I'll let you guys work on this. Let's do CH4. This is methane. It's found in natural gas. See if you can determine the Lewis dot structure for methane. How many valence electrons for carbon? 4. Does that look right? No, we want to fill out all 4 sides. There we go. Hydrogen, I'm going to put 1 on each side. We said it has 1 electron. It's pretty easy for this one, right? Pair up this, 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 and this. How many lone pairs do we have? None. So some compounds will have lone pairs, others will not. It really depends on the Lewis dot structure. Yep.
So if this was like on the test, how would you want to show it? Would you want it like the first way or both ways?
If I said Lewis dot structure, I would prefer it in this way. However, if you had dots instead of a line, I'd be fine with that too. So let's take a look at a little bit more complicated examples. And these involve multiple bonds. So some atoms share more than one electron. Okay, so let's take an example of this. This was from our previous lab, our oxygen lab. So we've got O2. Oxygen always exists as O2, not just O. It's unstable as elemental O. It has to be paired with another oxygen. So let's do the Lewis dot structure for one oxygen. How many valence electrons? 6. Okay, so 1, 2, 3, 4, 5, 6. I'll do another oxygen over here. 1, 2, 3, 4, 5, 6. You could say, okay, these two have got a pair. But then down here we've got these unpaired electrons. They really want to be paired, right? So all they're going to do is reach over and pair with one another. So now if we draw the Lewis dot structure, we've got an oxygen with 2 bonding sets of electrons, like that. And then each oxygen has 2 lone pairs left over. So I'll draw them out like this and like that. You can do them to the sides and kind of evenly distribute them. Does that make sense? Or what was your question?
That was saying, so it's a double bond?
Yep, so in this case, you're exactly right. This would be referred to as a double bond. Let's do another one. Going back to Fritz Haber, he was able to make ammonia or artificial fertilizer out of nitrogen gas in the air. Nitrogen makes up about 80% of our air, but it was a pretty big challenge converting that to useful ammonia. Let's try to figure out how to turn this into a Lewis dot structure. So we got 2 nitrogens. How many valence electrons? 5. So I'll go 1, 2, 3, 4, 5. Another nitrogen over here. 1, 2, 3, 4, 5. How many bonds do you think we'll have? 3. So we can say, all right, these are paired. These are paired. These are paired. So nitrogen contains this triple bond in between 2 nitrogen atoms. All right. You guys want to see another war gas? All right. My other class makes fun of me for all my morbid examples. So this is COCl2. This is also known as phosgene. This stuff's really nasty. They use this in World War I, and when you inhale it, it will react with the water in your lungs and the water on your eyeballs to make hydrochloric acid. So you were basically inhaling acid that would eat away at your lungs. This is super duper nasty stuff. Again, it wasn't super effective at killing people, but it obviously scared them, right? If you start breathing in acid, you're going to be freaked out and probably run away. So carbon is the center atom. How many valence electrons? 4. So 1, 2, 3, 4. I'll put an oxygen up here. We know we've got one of them. Yep.
Do you always want carbon to be in the middle if it involves a carbon?
That's a good question. So carbon really likes to be at the center of things. It prefers to be at the center if at all possible. So oxygen, how many valence electrons? 6. So 1, 2, 3, 4, 5, 6. All right, we've got some chlorines down here. How many do they have? 7. So I'll go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now we've got to pair these up. Okay, so the chlorine only has one unpaired electron. So it wants to pair that up with one of the carbon electrons. Okay, and then what about the oxygen? We can pair up this, and are we done? Yeah, we've got to pair up all of our electrons. Okay, so now let's draw this using Lewis dot structures. So carbon in the center. We've got a double bond up to oxygen. we've got these lone pairs. I'm just going to evenly distribute them around oxygen. And then over here, we've got a chlorine and a chlorine. I'm going to kind of keep them as far apart from one another as possible, and we'll talk about that tomorrow. And they've got these lone pairs still hanging out around them. And they've got 3 different lone pairs around each chlorine. So this would be our Lewis dot structure for the war gas phosgene. All right, I think we're going to leave it there today. But when we come back tomorrow, we'll talk about Vesper theory, and I've got some hands-on activities for us to do.